Hi there, my name is Jose Alejandro Lemus, and today I am presenting my project called A Critical Evaluation of Machine Learning Algorithms for DDoS Attack Detection in Cloud Environments. I am part of the school competing in the National College of Ireland 2025 in a master research project of cybersecurity. What are DDoS attacks? A distributed denial of service attack is a malicious attempt to disrupt the normal traffic of a target server, service, or network by overwhelming it with a flood of internet traffic from multiple sources, often using compromised devices forming a botnet. Why are cloud environments especially vulnerable? Cloud systems are publicly accessible, highly interconnected, and support elastic scalability, traits that attackers can exploit to amplify the effects of a DDoS attack. Their dynamic resource allocation makes it difficult to distinguish between legitimate traffic spikes and malicious loading, especially during flash ground events. The motivation of the study is because with the growing dependence of cloud infrastructure and the frequency of DDoS attacks are increasing, traditional detection mechanisms are not enough to mitigate these kind of attacks. We urge to detect them efficiently, and in order to that, this study critically analyzes the performance of supervised machine learning algorithms in detecting DDoS attacks within cloud environments. The goal is to identify which models offer the best balance between detection accuracy and computational efficiency for real-time implementation. The limitations are that not just the signature-based detection relies on predefined patterns. Anomaly-based detections often generate high false positives, and these approaches struggle to distinguish legitimate traffic surges, for example, flash crowns, from actual attacks. So we need for innovation. Increasing attack volume and complexity demand more intelligent, adaptive, and scalable detection systems. Machine learning presents a promising solution by learning from protecting from traffic patterns and detecting previously unseen behaviors. The primary aim is to conduct a critical evaluation of supervised machine learning algorithms for detecting DDoS attacks in cloud-based infrastructures. So in order to get that, we're gonna evaluate the detection performance of 4 machine learning models: random forest, support vector machines, gradient boosting machines, and k-nearest neighbor, to compare models using key metrics like accuracy, precision recall, F1 score, AUC, and execution times. Assess each model suitable for real-time deployment based on classification performance and computational efficiency. Our methodology is to we got a data set of CIC DDoS 2019 over 19.1 million records got from a Friday afternoon work, simulating a real world DDoS attack traffic like as TCP protocols, UDP, and others, reduced to 225,691 randomly selected records for performance optimization. On the pre-processing steps, we have removed null, missing values, and clean data, perform feature selection and standardization, balance dataset using oversampling techniques, save clean subset to process dataset.csv, and for the environment, it was chosen Google Colab as a cloud-based Jupyter notebook. the model training and evaluation, we have split the dataset into three parts: 60% for training, 20% for validation, and 20% for testing. Our models are random forest, support vector machine, gradient boosting machine, and k-nearest neighbor. And as we mentioned before, accuracy, precision, recall, F1 score, AUC, and the execution times are the metrics that we're going to measure each model. What this research focus is on for widely adopted supervised, as we said before, for binary classification tasks in cybersecurity. So random forest as an ensemble learning method using multiple decision trees for high accuracy and robustness to overfitting. Support vector machine is a powerful classifier that finds the optimal boundary hyperplane between classes, ideal for high dimensional data. Gradient boosting machines, a boosting algorithm that builds models sequentially, optimizing performance and minimizing error previous iteration. K-nearest neighbors means a simple non-parametric model that classifies based on the closest training sample in the feature space. Why these models? Making a comparison between these models, we find like random forest, we have a high accuracy and reliability as well as gradient boosting machines. SVM, a support vector machine, we have strong in precision and handling complex boundaries. K nearest neighbors, we have high interpretability and strong pattern recognition. The goal is to critically assess their efficacy, execution time, and detection reliability for cloud-based DDoS mitigation. And here we have the equations that we have for accuracy, precision, recall, F1 score, and area under the curve that we have here. And then we are going to use the confusion matrix in order to see what are the true positives, the true negatives, and instead to see the performance of each model. Under results, we found that random forest we have on the accuracy it's 0.9992, on the precision we have 0.9982, on the recall we have 1, on the F1 score we got 0.9991, and the area under the curve we found 0.9993. On the execution time when we test this, it was 362 milliseconds, so it's a little time to consider. Then on the other hand, we have the confusion matrix of support vector machine. We have with high numbers for true positives and true negatives. As we see the accuracy, we can see it's 0.9993, precision is 0.9996, recall is 0.9987, F1 score we got 0.9992, and the area under the curve we got 0.9992. For the model execution time we got 290 milliseconds. The results for gradient boosting machines, we can see it here, and then we have true positives and true negatives high. So the accuracy is 0.9928, for the precision is 0.9857, recall it's 0.9979, F1 score we got 0.9917, and the area under the curve we got 0.9934. For the time execution we got 276 milliseconds. So the results for k nearest neighbors we got 0.9996, then the precision we got 0.9995 on recall as well, on F1 score 0.9996, and then area under the curve we got the same. The only issue that we have on this one is the execution time. It's 1 minute 9 seconds and 204 milliseconds. So this is the model that it has consumed more time on detecting DDoS attack. And then making a comparison between the four analyses that we have done before, and then seeing in one slide, we can see in resume that KNN has best accuracy, but it's the slowest. Then for random forest is well balanced. For support vector machine is very precise, and then for the gradient boosting machine is fastest but slightly slower in precision. So the best one is KNN, but unfortunately due to the time execution, I will say that random forest is the well balanced, is the best option without consuming much time. And then could be SVM is very precise for support vector machines. As we can see here, the graph about these metrics that we have here, and then to make a comparison of them, and then having here the models and all the metrics and measures that we have done before. To getting a conclusion on this project is this study evaluates the effectiveness of the four supervised machine learning models, as we say before, and we have seen before the numbers that we got on each one. The key findings is all models achieve high accuracy, with KNN performing best overall. Then the random forest deliver a strong balance of precision and execution speed. Then support vector machine show exceptional precision and first training time. And then for the gradient boosting machine was the fastest to train, offering a practical solution for rapid deployment. Then the core insight is the machine learning offers a scalable, accurate, and adaptable approach to real-time DDoS detections. And then for future work is to incorporate deep learning, exploring models like RNNs or CNNs, or real-time deployment to implement these into a platform in order to check what are to explore in deep the application of this and the practicity that we have here. Then the semi-supervised and unsupervised approaches that we can look forward, like we can do in further discussions. Then the hybrid detection frameworks to combine machine learning with traditional techniques as rule-based in order to make a amalgam of these tools that we can offer. And then the advanced feature engineering integrate features based on entropy and other models and other theories that we can implement over this. And thank you for all. We have finished our critical evaluation of machine learning algorithms for DDoS attack detection in cloud environments. Thank you for all.